Gibson here. Today we're going to begin a new unit on Newton's laws of motion, and today's lesson looks at his first law of motion, sometimes known as the law of inertia. So let's look at our objectives. The first is to talk a little bit about key contributions in history to the science of motion, what led up to Newton's laws of motion. The second is to look specifically at Newton's first law of motion and what its implications are. And then third, we're going to distinguish between mass and weight and their units of measure. So let's talk about Nicholas Copernicus. He came a bit before Newton, about 100 years or so, but he was most known for his proposal that Earth revolved around the sun. And the conventional thinking up until that time was that the Earth was the center of the universe and everything revolved around it. Here's a little sketch from his notebook. You can see the fourth planet out there from the sun is Terra, or Earth, and the other planet. So he developed this concept through his observations of the planets in the sky. So his assumption was that there must be some type of force that controls an object's motion, and that an object in motion would require a force to be in place. So if there was no force, there could be no motion. Galileo then came along. He was a little more of a contemporary to Newton, and he began to do a lot of experiments with moving objects and their masses. So the first experiment we're going to talk about is one he did with rolling objects. Now he took a ball, let it roll down a platform across a flat table surface, and then back up the other side. And what he noticed is that the ball accelerated going down the ramp. So as it went in the same direction that gravity was pulling, it went faster, it accelerated. As it moved up the ramp against the direction of gravity, it slowed down or decelerated. And he noticed along the surface of the smooth tabletop where there was no ramp, assuming that there was no friction, he saw that the ball pretty much maintained a constant speed. So what he began to notice is that you don't necessarily need to have a force in order to have an object in motion. Definitely there was a force acting on the ball when it was going down the ramp or up the ramp against gravity, but not when it was traveling across the horizontal tabletop, yet it continued to move. So when gravity or friction is present, force is needed to keep an object moving. And he came up with this property called inertia. That is simply an object's resistance to change in its state of motion. So the greater the inertia of an object, the greater force is required to get it to change its motion. All right, so along came Newton, about the year that Galileo died. He was quite the Renaissance man. He was a physicist, a mathematician, astronomer, philosopher, and even a theologian. In 1687, he published his 3 laws of motion and the universal law of gravitation at the ripe old age of 25. And here's what his first law of motion says. An object that is at rest will remain at rest, and an object in motion will remain in motion. And then if, and this if is very critical to the first law, if there is no net force acting on the object. Now, a shortcut for that is simply objects keep on doing what they're doing. If they're at rest, they remain at rest. If they're in motion, they remain in motion, unless a net force is acting on the object. All right. Thank you, Sir Isaac. Now, what do we mean by force? We've used that term here already. We're going to work with forces a great deal here going forward. But we can often think of force as a push onto an object, right? If we're pushing or rolling this rock up the hill, obviously we're applying a force to it. We could apply a force through a pulling action, right? Put a rope around somebody and pull on it. That would be a pulling force. So let's define force. It's simply a push or pull on an object that causes a change in the motion in either speed or direction. So remember, speed and direction make up velocity. So basically, applying a force to an object causes a change in its velocity, which means it causes it to undergo acceleration. Now, force is a vector quantity. It has both magnitude and direction. And forces can be put into two categories, contact or field forces. So let's look at some examples of these and see if we can identify which type of force it is, a contact force or a field force. So let's talk about friction first. Two objects sliding together, right? There's friction between the two, or you rub your hands together and you feel the frictional force as they warm up. So would that be a contact force or a field force? Well, it turns out to be a contact force, right? Two surfaces rubbing together. Tension, pulling on a rope. Well, that is formed through the contact of the rope. How about gravitational force? Well, there's no solid object that's needed to convey the gravitational force, right? We know gravitational force can act through the atmosphere, through solid objects, through the vacuum of space. So this is an example of a field force. Now, normal force. Normal force, we'll talk about that a little more as we go forward, but a normal force is the force that opposes gravitational force. So if you set a book on a table, gravity is pulling that down, and the normal force is pushing up on the book. So it's the table pushing up on the book that creates that normal force. So because it's in contact, that definitely would be a contact force. How about a pushing motion on an object? That would be a contact force. How about electrical force? Well, we'll study this more in the spring, but electric forces are conveyed through electric fields, similar to gravitational fields. So that would be a field force. How about a spring force, right? Pushing and compressing a spring or stretching a spring out. That would be a contact force. And then a magnetic force, right? We've experienced this before. Take two magnets and bring them close to each other. We can feel the magnetic force that's conveyed across the air between the two magnets. So that would be a field force. And then air resistance. Now you might say, well, there's no objects in touch, but there actually is, right? Air resistance is the rubbing together of the air molecules against the object that's traveling through the air. So that actually is a contact force. All right, so again, we'll be working with forces a lot in this unit, but this is kind of an introduction to define what a force is and the different types of forces that we'll be working with. Now, Newton's second law says, the last part, the most critical part, unless there is a net force acting on an object. So what do we mean by net force? Net force is simply the vector sum of all the individual forces acting on an object. And by the way, the unit of force that we use for in physics in the English or SI system is called the Newton. Okay, and we just use a capital N as abbreviation for that. So that is the way we quantify how much force is being applied. So let's look at three examples here. These are what we call free body diagrams. We'll talk in more detail in future lesson about them, but they show that an object has certain forces being applied to it. So if we look at the three cases here, they all have an object that is pulling, or rather they all have a force that is pulling down the object by a force of 20 newtons. And then the upward force is different, right? The first example on the left has an upward force of 20 newtons. So the question is, what is the net force? Or another way to ask the question is, are these forces balanced? So if we look at the first example, if we have 20 newtons pulling down and 20 newtons pulling up, they're equal but opposite direction. So the net force, if we combine those together, add them as vectors, is that they will cancel out. So in this example, we would say we have a set of balanced forces and the net force is 0. How about the middle example? Well, if we have 30 newtons pulling up and 20 newtons pulling down, if we add those together, the net force would be the same as if we had a single force of 10 newtons pulling upward. So in this case, we would call that unbalanced. There is a net force of 10 newtons in the upward direction. How about the last case here? Well, we have 20 newtons pulling down, 10 newtons pulling up. So we would have a net force of 10 newtons in the downward direction. So this also would give us what we call a unbalanced condition, or a net force of 10 newtons down. Okay, so again, Newton's first law says objects stay in motion or stay at rest as long as the force is balanced. In other words, there's no net force. The net force is 0. But if it's unbalanced, then that's not going to hold true. Objects are not going to stay at rest, or they're not going to stay in motion if there's an unbalanced force being applied to them. All right, so we mentioned inertia. It's this characteristic of resistance of any object to change its state of motion. And the measure of inertia is simply the object's mass. The more mass it has, the more inertia. And it makes sense, right? The more mass an object has, the greater the effort or force is to cause it to change its motion, whether to speed it up or slow it down. So let's look at an example here, right? We've got an elephant and a mouse. Clearly, the elephant has much more mass and therefore much more inertia than the mouse. So when they collide, of course, the motion of the elephant changes very little, whereas the motion of the mouse with much less mass changes drastically, right? It actually changed the direction as well. So we would say the elephant has much greater mass or inertia. It takes more force to set the elephant in motion. It takes more force to change the elephant's motion. Now, we use mass a lot in physics as a term, but we also use the concept of weight. And often these two are used interchangeably, but that is not correct in physics. Mass and weight are two different things. So let's define them. Mass is the amount of matter in an object. It depends only on the amount and type of particles that make up the object. So for example, how many atoms of a particular element make up an object's mass, right? That is ultimately what determines the mass of an object. Now, the standard units that we use are kilograms in the SI system. In the English system, the mass is actually referred to as the slug. Okay, we don't hear that very often, but we certainly hear kilograms a lot. So again, mass is the measure of the object's inertia, and it's simply based on what is the material made up of. Excuse me. Weight is different. Weight is the force on a body due to gravitational acceleration. So it depends on the object's location and the object's mass. So you can see the formula for weight is quite simple. We take the mass and multiply it by the acceleration. Or if we use the symbols, W for weight, small m for mass, and G for the acceleration due to gravity. So in the SI system, the units for weight are newtons. So weight really is a force. It's just a specific force due to gravitational pull or acceleration. And in the English system, we refer to weight as the pound, right? And we're very familiar with that. That's typically how we express our weight in everyday life. Now, how do they compare? Well, 1 Newton is about 1/4 of a pound. So we have a good feel for what a 1/4 pound is. So that can help us to understand how much 1 Newton would be. It'd be about a little over 4 pounds would make up, a little over 4 newtons rather would make up 1 pound. Okay, so a Newton is less than a pound. or here, yeah, here's the ratio here. 1 pound is equal to almost 4.5 newtons. Now, mass, as we mentioned, is an absolute property of the matter. It depends on what it is made up of. Weight, on the other hand, is relative, right? The weight of an object depends on where it's located. Now on Earth, right, if we have 1 kilogram of mass, what will its weight be? Well, the mass is 1 kilogram. The acceleration due to gravity is 10, right? 10 meters per second squared. So we multiply those together and we get 10 newtons. On the moon, because the moon has a smaller mass, its gravitational acceleration is less than Earth. It turns out to be about 1/6 that of Earth. So that same mass of 1 kilogram on the moon would weigh about 1.6 newtons. Now in space, if you were far, far away from any sizable objects, so you were far away from the influence of gravity, you would say, okay, if the gravitational acceleration is 0, therefore the weight of the object would be 0. And this is where the term weightlessness comes from when you are in space. Okay, and we'll talk about that more later as we get a little bit more into Newton's particularly second law of motion. All right, so that's the lesson for today. We've identified the key contributions in history to the science of motion. We can state Newton's first law of motion, right? An object at rest stays at rest. An object in motion stays in motion unless there is a net force acting on it. If there is a net force, it'll cause an object at rest to speed up and accelerate, or it could cause an object in motion to either speed up more or slow down and eventually stop. And then the third is a distinction between mass and weight and their units of measure. So we know that mass is a property of the material based on how much and the type of material it contains, and weight is a relative measure based on the location of the material and the acceleration due to gravity at that location. All right, that's it. So there is a lesson there, or assignment rather, that goes with this, a Google quiz or form that you can use to answer questions and explore these concepts a little more. Thanks.